Good morning, guys and gals. Yeah, I think guys is a pretty neutral term. Well, what do I know? I mean, I don't. English is not my mother tongue. So anyway, so we're gonna continue, right? So we pretty much covered dielectrics, right? I'm gonna use this lecture now to introduce a bunch of terminology or jargon that is associated with dielectrics, and the jargon is as follows. So we can classify materials as linear. We can classify materials as dielectric materials as homogeneous. So the concept is called homogeneity. And then we can classify materials as dielectric materials as isotropic. So the concept is isotropy. Okay, so this sounds like arcane jargon, but it has a specific meaning that is simple to explain, and I'll explain it shortly. And then finally, we have to talk about dielectric strength, and then start talking about interface conditions. Okay. This is a table taken from the textbook that shows the dielectric strength of a bunch of material, right, in Kelvin per meter. So what's dielectric strength? Let's start there. So we said, I mean, the basic result that we got is that the flux density for any material is going to be related to the electric field intensity by the permittivity, right? And D is a measure of the polarization. D is can be written as the polarization of the underlying free space, right, plus the polarization due to the material. We established this fact. Right. Now, the interesting thing about the polarization due to the to free space is that this is a theoretical construct. So this is a theoretical construct, right? So we can, I mean, in theory, we can have as big of an electric field as we want, and the polarization in free space will not break. Meaning that if I have a polarization vector in free space, so I'm gonna draw the polarization this way, no matter how big the electric field gets, there is no point where in the theory at least, there's no point where E becomes so big as it approaches infinity that those dipoles break, meaning that the positive and negative portions break and separate, and those bound charges turn into free charges after the dipole breaks due to the intensity of the field. Right? So that never happens, at least in the classical theory. Right? Of course, classical electrodynamics is not valid for very large E. So if E as approaches infinity, as I've written here, the theory itself is not valid anymore. We have to bring in more modern theory, right? But I mean we have to reach really a stupendous field value for that quantum effect to even matter. So we don't need to think about that in terms of the classical theory. Right? However, for materials, for the polarization that arises to the material, it's possible to break the material with a big enough electric field intensity. Right? So on top of free space, there are the dipoles on the material themselves, in the material itself, right? Those dipoles, those are actual nuclei and electrons around the nuclei, right? So it is possible to break those atoms if we have a large enough electric field. And the electric field intensity where those atoms in the material break is the dielectric strength of that material or of that medium. So this is the concept of dielectric strength, right? And this table from the textbook shows the dielectric strength of a bunch of different materials, right? So for example, for air, it's 3 times 10 to the power 6, which is 3 million volts per meter, right? Meaning that the potential difference, if you have 1 meter of distance, the potential distance, the potential difference, or the voltage between those 2 points, like this voltage, that is enough to ionize the air molecules, cause the atoms in the air to break and the electrons and protons to start flowing freely, meaning the air turns into a plasma. That voltage is 3 million volts. If you have 3 million volts per meter, that's enough to turn the air into a plasma and break the dielectric material that is the air. Right? Of course, you can scale it down. Like, let's say if you're interested in 1 centimeter, once a meter has 100 centimeters, right? So this is 1 centimeter, right? In this case, the dielectric strength is 1/100th of this, right? So the meter has 100 centimeters, so it's going to be, so this is 3 million over 100. This becomes 30,000 volts per meter, right? So this is, and typically you are given the dielectric strength of air as this value. It's given as 30,000 volts per meter, right? One aspect where you can, application where you see this being important is in PCB design. If you're designing a PCB board with a bunch of components on the boards, and let's say hypothetically, your voltage is like 1,000 volts. You're handling, this board is handling voltages of 1,000 volts, right? That tells me that, hey, the distance, even the air, right? So even though I have two components with air between them, I have to be careful with the distance between those two components. This is called creepage and clearance, right? Creepage and clearance. And let's say 1,000 volts, right? So, okay. So the question is, how much distance, minimum distance do we need to have to accommodate the 1,000 volts voltage difference, right? So so this is 3,000 volts per meter per centimeter, right? So this is 3,000, no, not 3,000, 30,000 volts. I need to correct this, per centimeter. Volts per centimeter, right? So I can invert this, that's 1 over 30,000 centimeter per volts, right? Times 1,000 volts, which is the voltage difference I'm designing the PCB for, right? That gives me volt over volt. That gives me 1 over 30th of a centimeter. That's the minimum distance. 1 over 1, right? So that's what? That's 0.1 over 3. That's 0.0333 centimeter, or 0.3 millimeters. I cannot have the distance between any two components be less than 0.3 millimeters, for example, if I want my design, if I don't want to get arcing through air, right? So that's where the dielectric strength plays a big role in, In vacuum, it doesn't matter. I can have as big of an electric field as I want, but real life materials, right, there's no pure vacuum unless you're in outer space. You're very close to a vacuum. We have to be, I mean, for real life applications, we have to be aware of the dielectric strength of different materials. Right? Some materials have stronger dielectric strength than air. For example, mineral oil, wax paper, even paper has like an order of magnitude larger dielectric strength. Right? Diamond has a very good dielectric strength. So it's what? It's like 6, 7, 8, 9, 3 orders of magnitude, 1,000 times stronger. Of course, the vacuum has a hypothetical 10 to the power 18, right? So this is like a hypothetical dielectric strength. What happens actually in the vacuum is interesting. It's more of a becomes a more of a quantum effect that starts to play a part when you reach those really large, humongous electric field strengths, right? So it goes beyond, things go beyond the classical theory. That's why there's like a finite. You would expect within the classical theory the dielectric strength to be infinite, right? But it's not. It has like a very large value. It's still let's see, 6 and so it's 18 minus 6. It's 12 orders of magnitude larger than air, right? So it's 12 orders of magnitude larger than air. That's really tremendous, right? Each order of magnitude is multiplication by 10. Right? So it's like a million times larger, stronger than air. Okay, so this is the concept of dielectric strength. Let me now touch upon those 3 words. What do they mean? Linear. What does it mean to say that the material is linear, right? So the material is linear, I mean, if the permittivity does not change, is constant versus E, right? The magnitude of E. So we know that D equals epsilon E. If epsilon remains constant regardless of what the value of E is, we say the material is linear. One way of looking at it is that if we plot the magnitude of D versus the magnitude of E, it's going to be a straight line for the material, right? So that the slope is going to be epsilon. That's essentially what a linear material is. Pretty straightforward. And then, of course, we know that after a certain point, if E is large enough, the material just breaks. So this is where we get the breakdown at some point. But before the breakdown, the material is pretty linear. If I had something like this, you know, the material is not linear. The material is, the epsilon is varying depending on how strong E is. That doesn't happen in the dielectric materials, right? In most dielectric materials. Okay, so that's linearity. Homogeneous. What's homogeneity? Homogeneity means that epsilon does not depend on location within material, right? It doesn't matter where the electric field is. Like this cube is a material. It doesn't matter if the electric field is here, or it's at this point, or at this point, or it's this point, right? Epsilon is going to be the same, right? So that's when the material has the properties. It doesn't matter where we apply the electric field, we're going to get the same epsilon. That material is homogeneous. That's homogeneity, right? Isotropy essentially says epsilon does not depend on direction E, the electric field intensity. Meaning if I have some slab of material, doesn't matter if I apply the electric field in this direction or I apply it in this direction, right? I will get the same epsilon, right? The relationship between D and E will be the same, right? Let's say this is E1 and this is E2, then D1 equals epsilon E1 and D2 equals epsilon E2, and those two epsilons will be the same, right? If a material, it's possible to have materials where the direction of the field changes epsilon, but those kind of materials are not isotropic, right? The materials that we'll be interested in studying, so this is what isotropy is. The materials that we are interested in studying, and that are the most common kinds of materials, are linear, homogeneous, and isotropic. They have those three basic properties. Those kind of materials are called, you can see it, right? Simple materials. Right? Other kinds of materials exist that might be linear at a certain range, but not linear all the way. Might not be homogeneous and might not be isotropic. Those kind of materials exist, right? But a lot of materials for a certain range of E are really simple materials, and we can always assume that linearity, homogeneity, and isotropy applies for those materials. Right? The materials in the table here are mostly linear, homogeneous and isotropic. Right? Some specialized kind of crystals are not, but typically most materials you can assume they are linear, homogeneous, and isotropic, unless you are told otherwise. Right? I don't think we will not encounter those materials within the scope of this course, but you have to know that they do exist, and they do offer like a lot of interesting properties that are they offer an interesting field of study. It's a big field of study, the properties of materials under electromagnetic fields. All right. Now I want to jump to the topic of interface conditions. Right, so we have a reasonably detailed theory of the medium where electromagnetic fields, particular electrostatic fields exist. We still haven't discussed magnetic fields, right? But we have a pretty solid theory of the medium as a space where polarization occurs, and that gives rise to the permittivity, right? Susceptibility, electrical susceptibility, polarization vector. Those are all concepts that we studied. Charge distribution density due to polarization, volume charge density due to polarization, which is something like this, right? Which is this. Surface charge density due to polarization, rho ps, where n is the normal vector at the boundary of the n hat is a normal vector at the boundary of the material or medium. Okay. So we covered all those concepts. For a particular medium, the medium could extend in space, right? Or the medium could have a finite volume. What happens if the medium has a finite volume? Well, what will happen is that that will mean that this medium will have a certain permittivity, but then there will be a boundary, and beyond this boundary we'll have permittivity of epsilon naught, which is the permittivity of free space or empty space. So there is an interface between the two, right? So within the confines of the theory, what could happen is that we could have a certain medium with a permittivity of epsilon 1. Then we will have another medium adjacent to it with a permittivity of epsilon 2, and there is an interface, a boundary between them, a border between them. So the question is, what is the effect of this interface on the electrostatic field, both in both its manifestations as electric field intensity or flux density, electric flux density. Right? So this is material 1, and this is material number 2. Right? So how does E vary at the interface? Does E remain continuous? Is there a discontinuity in E? How does E just before the interface relate to E just after the interface? We already studied a bit of that when we discussed the interface between empty space and a conductor. Empty space is a kind of dielectric material, right? Air also is a kind of dielectric material. So we already discussed that. We said that E is 0 inside the conductor, and then E is gonna always be normal to the interface outside the conductor. So we covered a bit of that. Now we're gonna discuss a more general problem, which is the case when we have an interface between two different dielectric materials. Right? So those are the two questions we want to answer. We answered question 2 already, but we're gonna summarize it, right? But question 1 is, what happens if we have interface between two dielectrics? This situation, epsilon 1, epsilon 2, and then dielectric and conductor. Right? So I have an epsilon and then a conductor. So the short answer is that we apply the postulates at the interface. The postulates and one of the results we got about the polarization at the interface, mainly this result, that the charge density due to polarization at the surface charge density due to polarization at the interface is just the polarization vector dot n hat, which is the normal vector to the interface. Okay, so let's start with the tangential components. Right? The idea here is the following. We have this interface, let's say, and it extends this way. I'm zooming in on the interface, and then I have material 1, then I have material 2. The idea is that the electrostatic field, which I can represent by either E or D. I mean, E or D are the same representations of the different representations of the same thing. E is looking at the electric field from the point of its force intensity. That's why we call it the electric field intensity. If I put a test charge there, how does the electric field move it? And D is looking at the electric field from the point of its flux density, from the perspective of its flux density, right? It essentially means how much polarization is occurring in the medium due to the electric field. So although like they look different, they are manifestations of the same thing. They are representations of the same thing. It's like two different faces of the same coin. Right? So I could either put E here or D. So the point is that close to the interface, just as before I hit the interface, in the medium 2 I have some E2, and then just after the interface I have some other, let's say it's different, let's assume it's different, let's be the most general, right? It could be the same field, but let's assume it's slightly different. So this is E1, right, just after the interface. The idea is that just before the interface and just after the interface, we can always decompose the field into two components, into a component that's tangential, to a component that's tangential, like this. So this is E2t, and this is E1t, the tangential. The magnitude of that tangential component is called E1t and E2t. So those are the components that are parallel to the interface. And then there are normal components that are normal to the interface, right? So I'll draw it this way, right? So this is E1n, and this is E2n. Okay, so I need to have a sense of which direction is going to be the positive normal and which direction is going to be the negative normal. So typically what I do is I assume that there's a certain unity normal vector, and that gives me what I consider to be the positive direction. So if any normal component is in this direction, it's going to be positive. If it's in the opposite direction, it's going to be negative. Right? That's all that this is doing. I'm defining where the positive normal direction is. Right? And then the tangential, let me call this, I mean, this is not very important, but let me call this t hat, tangential unit vector. I mean, I'm assuming the right hand rule, right? So it's going to be in this direction, right? So the idea is that we can, the field just before the interface and just after the interface, we can both those fields decompose them into two components. Component tangential to the interface and a component normal to the interface, right? So, and it's good to do that now because now we can examine the transition in the field, the change in the field for both the tangential and normal components. And once we know the transition for both, we can just add them up to get the total transition. Okay, so starting with the tangential component, what can we do to figure out what happens to the tangential component? Well, what we could do is we can apply the first postulate, which states that cross E equals 0. This is a differential form, and then the integral form is that the line integral over some curve C E dot dl equals 0. So remember, this is the first postulate. Okay, so there's a trick to applying it. How will I apply it? So this is the interface, epsilon 1, epsilon 2. I will apply it I will make I have to select what my curve is going to be. So I'm going to select the curve that minimizes the normal components. I want to ignore the normal components. I want to only examine the tangential components. So I need to pick a curve that's like a rectangle, like a long rectangle that's very thin. Why do I want to make it very thin? So that I can ignore the normal components, because the width of this rectangle is gonna capture the normal components. I want to ignore those components, so I want to make this width very thin, this one, right? This is my curve that I'm gonna integrate over, right? And I'm gonna do a limit in this case. I'm gonna take the limit such that this width approaches 0. Okay, so the idea now is that if this is E1t, right, and this is E2t, right? I'm assuming that I don't know what's it doing. Oh, okay. So yeah, I always have to assume what's the positive direction for the field, right? In the tangential dimension. So this is t hat, right? This is where if any field is in that direction, the tangential component is positive. If it's in the opposite direction, the tangential component is negative. So the idea is I can integrate over, so this is delta W and this is delta L. And the assumption is that delta W is approaching 0, so I can ignore that part. So if I apply the postulate, I get what? I get E1t times delta L minus E2t, because not I have to go clockwise along the curve. I don't have to, I mean I choose to go clockwise along the curve. C. So this is C. So I start from this point and I go clockwise. So when I go in this direction, I have E1t delta L. When I go in the opposite direction, I'm opposing the field, right? So I go, so the term is going to be E2t minus E2t delta L. The dot product here gives me a minus equals 0. That's the first postulate, right? I can remove delta L. I end up with the result that E1t equals E2t. So this is the first interface condition in terms of the tangent electric field intensity. So the electric field, the tangential component of the electric field intensity is continuous, meaning there's no jump in it as we move along the interface, as we cross the interface. However, the flux density vector is not continuous. Why? Because remember D equals epsilon E, so therefore E equals D over epsilon, but epsilon is different, right? Depending on the material. So this means that D1T over epsilon 1 equals D2T over epsilon 2. This is the first interface condition in terms of the tangential components of the electric field. Right? So the electric field intensity is continuous. The flux density for the tangential components, the tangential components of the flux density is not continuous. There's a jump in it that depends on how epsilon varies between the materials. Okay, so that's it. That's the result. Now we can jump to the normal components. How do the normal components of the field behave? Okay, so we have to remember, right? So I'm going to use D for this derivation. We have to remember that D is a polarization vector. Right? D is a quantification of the electric field using its polarization effect, while E is a quantification of the electric field using its strength. Right? And remember we got the results that if you have any material, I can deduce, and there's some polarization in it, I can deduce what's the surface charge density going to be on the boundary of the material by just taking, I take the normal on the interface of the material, on the boundary of the material, and the charge density rho PS due to polarization is just going to be P dot n hat. So we obtained this result in the past. So I'm going to use this result actually. So I have this interface. I have epsilon 1, epsilon 2. Right? And then I have, just before the interface, I have D2. This kind of polarization. Just after the interface, I have D1. I'm assuming they're different. They could be the same. I don't know, but for the more general case, I'm assuming they're different. Okay, so the question is, how does we know how the tangential component varies across the interface. Question is, how does the normal component vary? Right? So that will depend, right? So remember, there's this D2 is a polarization vector inside material 2. This is material 2, and this is material 1. Okay, D2 is a polarization vector in material 1. What does that mean? That means that at the interface, at the border of material 2, we're going to have a charge density that appears, right? Because all the polarizations are happening inside the space, and then they hit the boundary, and they manifest as a surface charge density at the boundary. Okay, so there are two charge densities on the interface. Charge densities that manifest due to polarization in material 2, plus the charge densities that manifest due to polarizations in material 1. Right? And adding those two gives us the total charge on the interface, right? Surface charge on the interface. So I should assume that there might occur in such cases. It is possible that we will encounter some charge density at the interface due to differing polarizations. So there's a complication here when we examine the normal component. There's a possibility of the existence of charge density at the interface. So I need to move forward now. So before I move forward, I want to use this result, right? I said I want to use this result. So I need to specify what is the positive direction for the normal component and what is the negative direction. So I could define my normal unit normal vector to be this, right? What does that mean? That means that the vector in the opposite direction is going to be minus n hat. Okay. And now I ask myself the question, what is the total charge on the interface? Right? So this is total surface charge density on the interface. Well, this total charge density is the polarization surface charge density due to material 2. So material 2 is polarized, and then it has an interface here, and there will be a charge density due to the polarization in material 2, plus the surface charge density due to polarization due to material 1, right? So the boundary is a boundary for two materials. So and each material is going to have its own surface charge density due to polarization. We just now apply this result that we got. Nothing complicated, right? So from the perspective of material 2, the normal to the interface to this material is n hat. So the surface charge density due to material 2 is going to be d2 dot n hat. What's the surface charge density due to material 1? Well, the normal vector from the perspective of material 1 is going to be minus n hat, right? So surface charge density due to material 1 is going to be d1 dot minus n hat, right? So I can do some manipulation. So rho s, right? I can take the minus out, so I end up with d2 minus d1 dot n hat is the surface charge density. This result gives me the interface condition, right? So I can ignore the tangential component, right? The tangential component dot n hat is 0, right? But the normal component is the component that gives me rho s. So the result that I get is that d2n minus d1n equals rho s. Okay. So the normal component in the flux density is almost continuous. It could have been continuous if there is no charge density that could manifest. But because the surface charge density could manifest, it is not continuous. There is going to be a jump in the normal component of the flux density due to the manifestation of a surface charge density. Now, when will a surface, that's an extra complication. When will a surface charge density manifest? That will depend on the problem. But you have to always be careful with the normal component. You need to ask yourself, hey, is a surface charge density manifesting? If it is, then there is a discontinuity in the flux density, normal flux density. Right. So this is the interface condition, and I can write it in terms of the electric field intensity as follows. I just, instead of d2n, I write epsilon 2 e2n minus epsilon 1 e2n equals rho s. Right. This is the interface condition number 2. Right. Be careful with the textbook. I think the textbook here is an error. I mean, it doesn't matter much. I mean, for many problems, you will discover that rho s turns out to be 0 sometimes, not all the time, by the way. So that might not matter, but you have to be careful with the sign. I think they messed up the sign there. Right. Always draw the n hat vector to tell yourself, hey, which is the positive? Where is the positive component, and where is the negative component? Right. When is the normal component positive, and when is the normal component negative? Same thing with the tangential. I typically assume the tangential positive direction to be, using the right-hand rule, to be like this, t hat. So it's always to the right. Okay. Yeah. So those are the interface conditions. Oh, by the way, this gives us this interface condition. Both of those interface conditions we can use to deduce a phenomena which will be familiar to you, called refraction. Actually, those interface conditions are the root cause of refraction. Refraction appears in optics, right? It's when you have a ray of light coming in, and then it refracts at a different angle. Let me draw this more clearly. Right? So typically, light keeps going in a straight line, but if it encounters a boundary, it refracts. Right? So this happens, the root cause of this happening is due to the difference in permittivity of the materials. Right? So this phenomena, the root cause of this phenomena is the change jump in epsilon. Right? And I'll show you how. So let me do the interface again. Right? And let's assume rho s equals 0. Again, I said this is dependent on the problem. Some problems rho s will not be 0. Many problems, actually, I would say rho s will not be 0, but many problems also will have rho s of 0. Right? So, but assume rho s of 0. Right? And then assume that the normal vector in the positive direction is this direction, and then tangential vector, positive direction of the tangential vector is going to be this direction, right-hand rule. Okay, so there's a material 1, material 2. Just after the interface in material 1, I have E1, and then just before the interface, I'm gonna, just to get my triangles easily, I'm gonna draw it this far, but it's just, imagine it just before the interface, I have E2. And I said this I can decompose into a normal component. So this is E1n, and this is a tangential component, E1t. Again, I can decompose this into a normal component, E2n, E2t, sorry, a tangential component, E2t, and a normal component, E1n. Now I want to define angles. I want this to be theta 1 and this to be theta 2. Right? So what's tan theta 1? Tan theta 1 is clearly E1t over E1n. what's tan theta 2? Tan theta 2 is E2t over E2n, right? And then let me divide the two together. Tan theta 1 over tan theta 2 equals E1t over E1n times E2n over E2t, and then we know the tangential components are equal, so this cancels out. I end up with what? E2n over E1n. Let me write that in terms of flux density. So this is equal D2n over epsilon 2 over D1n over epsilon 1. But we said because the rho s is 0, that means D2n minus D1n equals rho s, which is 0. That means D1n equals D2n. So this cancels with this, and I end up with this result. Tan theta 1 over tan theta 2 equals epsilon 1 over epsilon 2. So this is the main result for refraction. I think it's called Snell's law or something, right? Sorry, epsilon 2, right? So the ratios between the tangents of the angles can be determined simply by the ratios of the permittivities. If you know the different permittivities, you know how the angles are gonna refract. If you know theta 1 and you know epsilon 1 and epsilon 2, you know what theta 2 is going to be. And this is the root cause of the phenomena of refraction for light. Why does it apply to light? Because light, as I said in the beginning of the course, right, light is ultimately an electromagnetic wave. And yeah, finally the dielectric conductor interface. I mean, we already did that. I think we have the result, yeah. So if I have a material 2, that's a conductor, material 1, that's some material epsilon 1, right? E2, E1, and then the positive direction is this, right? So we already discussed this in a previous lecture. We said that E1t equals E2t equals 0. Tangential component is always going to be 0. That means that D1t equals D2t equals 0, right? And E1n equals rho s. The normal component is rho s over epsilon 1. Right, and D1n equals rho s. We derived this result using Gauss's law, and we could think of it as a polarization. So there's a normal polarization at the interface, and that results in a positive charge density. So those are the results. Okay. So to summarize, for dielectric to dielectric, E1t equals E2t, right? And the corresponding flux densities are D1t over epsilon 1 equals D2t over epsilon 2. This is a tangential component, and then the normal component is D2n minus D1n equals rho s, right? And then epsilon 2 E2n minus epsilon 1 E1n equals rho s. and then die conductor, right? E1 T equals E2 T equals D1 T equals D2 T equals 0. Everything equals 0 in the tangential domain. And then the normal domain is that E1N equals rho S over epsilon 1, and then D1N equals rho S. Right, and of course E2N equals D2N equals 0. There is no field inside the conductor. Material 2 is the conductor. Material 1 is the dielectric. Okay, so this concludes the discussion of interface conditions. Hopefully it's pretty intuitive at this point. So I'm going to stop here, and we're going to continue the discussion next lecture. Thank you, guys.